Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to lecture 19, and in this lecture we are going to discuss strain matrix in cylindrical coordinate system. So, you can recall that in the last two classes we derived the equations of equilibrium in cylindrical coordinate system, and the idea was to solve the deformation problem in cylindrical coordinate system. So, just as we found out stress and its equation in cylindrical coordinate system, today we like to know strain in this coordinate system, and later on we will relate stress with strain in this coordinate system. All right. Okay. So, let us begin with the definition for the strain tensor. So, you can recall from the earlier lecture that the strain tensor is simply half of grad u plus grad u transpose. Okay. So, that is the definition of strain tensor, and as it is a tensor, it is independent of the coordinate system. Then we wrote this strain tensor in the Cartesian coordinate system. Just to give you a recap, so that turned out to be the strain tensor when expressed in the Cartesian coordinate system, which is E1, E2, E3. So, this was del u1 by del x1, del u2 by del x2, del u3 by del x3, and then the off diagonal we had half of del u1 by del x2 plus del u2 by del x1, and then it is symmetric. Likewise, this term here is half of del u3 by del x1 plus del u1 by del x3, and then this is same as the term here, and finally, these two terms they were half of del u2 by del x3 plus del u3 by del x2. Okay, so, that is the strain matrix in Cartesian coordinate system, but we want to have the same matrix for the cylindrical coordinate system. So, to do that we have to first think of what is the formula for the gradient in cylindrical coordinate system. If you want to use cylindrical coordinates, what would be the formula for the gradient? Okay. So, you can recall that the gradient for any quantity, if we use Cartesian coordinates, then this was del over del x1 of that quantity tensor product E1 plus del over del x2 of the same quantity tensor product E2 plus del over del x3 of that quantity tensor product E3. So, that is the definition. Okay. So, we do not ask how it comes, it is simply the definition. All right. So, that is using the Cartesian coordinates x1, x2, x3, but if we want to use cylindrical coordinates, then we could write this as del over del r of the quantity tensor product E r plus 1 over r times del over del theta of the same quantity tensor product E theta plus del over del z tensor product E z. So, that is the definition using cylindrical coordinates, and you can see again that the derivative del by del theta is accompanied by this 1 over r term, right, because theta is non-dimensional and we want to take the gradient with respect to length. So, we have to divide by the radius. Okay. All right. So, now how to work this out now? See, we want to do it for displacement u. So, maybe we should write down u also in the cylindrical coordinate systems. Let us decompose u in the basis of cylindrical coordinates. So, u would become u r E r plus u theta E theta plus u z E z. So, u r for example, is the displacement in the radial direction. You know, if this is the body and here is a point of the body, this is the origin and this point has got coordinate r theta, then the displacement in the E r direction, that is u r, and the displacement in the theta direction, that is u theta, where the displacement in the z direction coming out of the paper, that is u z. Okay. So, we are simply decomposing the total displacement along the cylindrical basis E r, E theta, E z, and then we get u r, u theta, u z as the components. Okay. So, now we have to plug in this u in the formula above. So, wherever we have this bracket, we have to plug in the expansion of u within the bracket. All right. So, that means the gradient of u is del over del r of u r E r plus u theta E theta plus u z E z tensor product E r. So, that is the first term. Then the second one is 1 over r del by del theta of the same quantity tensor product E theta plus del by del z of the same quantity tensor product E z. Okay, let us work out the first term over here. So, see that the basis E r, E theta, E z, they do not change when we change the radial coordinate, is not it? You can recall that E r and E theta change only if the theta coordinate changes. So, when we do the derivative, E r, E theta, E z will act like a constant and then we only take the derivative of the components. So, the first one simply becomes del u r over del r of E r plus del u theta over del r of E theta plus del u z over del r of E z tensor product E r. Okay. So, that was quite easy. Likewise, for this third term here, we have to take the derivative with respect to z. So, again the basis vectors will not change because they change only when theta changes. So, this derivative is also easy and this is simply del u r over del z E r plus del u theta over del z E theta plus del u z over del z E z, and the whole thing is tensor product with E z. Okay. The middle one is the tricky one, because now we have to take the derivative with respect to theta and the basis is also going to change. Okay. So, this when we work it out, that would be, so first u r E r. So, both u r and E r change with theta. So, we will have two terms from u r E r, which is del u r over del theta into E r plus u r times del E r by del theta, and we know that is simply E theta, right. So, this becomes u r E theta. So, it gives me two terms, then the second one is u theta E theta. So, that is going to give me del u theta over del theta E theta plus u theta times del E theta by del theta, and that is simply minus of E r, right, pointing towards the origin. So, this is u theta into minus of E r, and then the last one is simply u z E z, and then E z we know that basis vector does not change at all. So, this is del u z over del theta times E z, and this whole thing is tensor product with E theta. And now you can see that we get two extra terms here. This is the first term and that is the second term. When we do the Cartesian gradient, we do not get these two terms, but with cylindrical coordinates, because the basis vectors also change, therefore, we get these two extra terms, and that is of course going to show up in the strain matrix. Okay. So, when we work out the strain matrix, how to populate the strain matrix now? So, let us first work out the displacement gradient matrix. So, displacement gradient matrix in r theta z coordinate system. So, its first row first column, that would be the component of the basis E r tensor product E r. Okay. So, to work this out, you can simply think of writing r theta z along the row and also along the column r theta z, and then this entry, for example, is the combination of r and r. So, it is E r tensor product E r. So, where is E r tensor product E r? So, we have the full gradient written here in the blue. So, E r tensor product E r, that is this term right here. You see it, del u r over del r of E r tensor product E r, and that is the only term. So, in the cross here we are going to write del u r over del r. Okay. Let us think of E theta tensor product E theta. So, where is that? So, you can see we have two of them here, and both of them will then show up here, and it becomes 1 over r of del u theta over del theta plus u r. Finally, for E z tensor product E z, so that is the term here. So, we will write it as del u z over del z. Okay. Now, what would be present at this cross? You see, this is first row second column. So, this corresponds to E r tensor product E theta, right. Now, let us have a look at where is E r tensor product E theta. So, we have to look at this expression, because this has the second one as E theta, and then its E r component. So, E r tensor product E theta, and you can see it is here and over here, right. So, in the cross over here, we would write down 1 over r of del u r by del theta minus u theta. You see we get a minus sign because it is u theta into minus E r. So, we have to likewise work out everything, and you see the displacement gradient, it is not a symmetric matrix. So, what would be E r tensor product E z? So, that is over here. So, this comes here del u r by del z. What is E theta tensor product E r? That is right here. So, this becomes del u theta over del r. What is E theta tensor product E z? That is over here. So, we have del u theta over del z. What is E z tensor product E r? So, that is over here del u z over del r, and finally, what is E z tensor product E theta? So, that is this remaining term, the only remaining term. So, we get 1 over r del u z over del theta. Okay, so, that is the displacement gradient matrix, and the strain matrix we know is half of grad u plus grad u transpose, right. So, the strain matrix would then be, so this implies the strain matrix in r theta z coordinate system. So, on the diagonal we will have the same as in the gradient of u. So, it becomes del u r by del r, then 1 over r del u theta over del theta plus u r and del u z over del z. Okay, and now this is symmetric. So, we have to only work out the upper half, let us say. So, the term over here, that would be 1 over 2 times 1 by r of del u r by del theta minus u theta plus del u theta by del r. Okay. And then this is same as this term over here. Then this entry over here, again it is formed by the symmetric component, and that is half of del u z over del r plus del u r over del z, and then this is same as the term over here, and finally over here we will have half of 1 by r del u z by del theta plus del u theta over del z. Okay, so, that is your strain matrix. And what are the unusual terms over here? So, we have to compare with the strain matrix in the Cartesian coordinate. So, this strain matrix here, the off diagonals, all of them have 2 terms, right. But here in the cylindrical coordinate we have extra terms. So, we can identify them. See, this is the extra term, likewise this is also the extra term. Okay. And again why it is arising? Because it is cylindrical coordinate system, the basis vectors are also changing. So, when you take the gradient, you also have to take into account the change in basis vector due to theta, right. Okay. Now, what are the physical meanings of each of the components over here? So, epsilon r r for example, so the one in the radial direction, it is simply epsilon tensor into E r dot with E r. So, that is a longitudinal strain in the radial direction, okay. And that is del u r by del r, and we call it radial longitudinal strain or simply radial strain. Okay. So, basically think of a radial line element and what is the elongation of that radial line element. So, we can also draw a picture. So, think of this cross section of a hollow cylinder. Okay, so, that is the cross section of a hollow cylinder. And any radial line element here would be a line element in the radial direction, and we are talking about the strain, the longitudinal strain in this particular radial line element, and that is epsilon r r. Okay. Similarly, epsilon theta theta. What is epsilon theta theta? So, that would be epsilon tensor E theta dot with E theta, and from our strain matrix that is a 2 component and it has got an extra term. So, this is 1 over r del u theta by del theta plus u r, and this has also got a name, this is called hoop strain. You could also call it as circumferential strain. Okay. And this is the change in length over length of a line element in E theta direction, or let us say of a circumferential line element. So, where is a circumferential line element? So, you have to think of a line element directed along E theta, and it has got epsilon theta theta associated with it. Okay. Can we somehow make out why do we get an extra term? Is there a physical reasoning to see why we have an extra term? See, the first term 1 over r del u theta by del theta, that is kind of intuitive, because for longitudinal strain we simply take the derivative of displacement in that particular direction divided by the coordinate in that direction, right. For example, epsilon r r is del u r by del r. So, both numerator and denominator are r. So, here it is del u theta by del theta, but why do we have this extra term? So, to understand that, maybe think of a displacement which only has got u r. Okay. So, think of a displacement having u r not equal to 0, but u theta and u z are both 0. All right. So, for such a displacement, what would be epsilon theta theta? So, in this particular case, epsilon theta theta is u r by r. So, that is the unusual term. Now, let us see why that should be the longitudinal strain or the hoop strain. So, again think of our hollow cylinder. So, we have this hollow cylinder and this is this cross section. So, cross section of a hollow cylinder, and think of a circumferential line in this hollow cylinder. So, this dashed line So, this is a line along the circumference of the cylinder, and say it is situated at radius r from the origin. So, after deformation, this line will then be at small r plus u r, right, because we only have u r as the displacement. So, after deformation, this red line will change to the blue dashed line. So, this is after deformation, whereas the red one is before deformation. And let us think of what is the longitudinal strain for this circumferential line. So, longitudinal strain epsilon would be delta L divided by the original length L. Now, what is the change in length? Final length minus original length. What is the final length? It is 2 pi times the final radius. So, that is 2 pi times small r plus u r, correct. So, you have to remember the change in radius. So, this green line is basically u r, right. So, the final length is 2 pi times small r plus u r minus the original length, which is 2 pi times small r itself, divided by 2 pi small r, and we work it out and we get simply u r by r, right. So, you see that is the strain, longitudinal strain of this circumferential line. So, that is your epsilon theta theta, right, the hoop strain. There is no u theta here, therefore, epsilon theta theta is equal to u r by r. So, this is epsilon theta theta. So, that is the physical origin of this extra term in the hoop strain. Okay. Likewise, we have another extra term in the shear strain corresponding to this entry here, right. So, that is epsilon r theta. So, what is gamma r theta then? It is twice of it. So, gamma r theta is 2 times epsilon r theta, and that is equal to 2 times epsilon E r dot E theta, which we know as 1 over r of del u r over del theta minus u theta plus del u theta over del r. So, this is telling me the change in angle between two line elements which are along E r and E theta. Okay. So, again you can draw the circle. Let us have a circle here, and at any point we can think of two line elements. So, this is the origin. So, one is E r and the other one is E theta, and we are talking about the change in angle between these two line elements. Okay. So, change in angle between E r and E theta, that is gamma r theta, the shear strain. Okay. And it has got this extra term minus u theta by r. So, I think you should try to figure out why we have this extra term. Maybe I will give an explanation for this in a solved example, okay, but in the meantime you should try to figure out. Okay. So, likewise you can think of physical meaning for each of the strain components here. We have gamma r z So, that is the shear strain between E r and E z. Similarly, gamma theta z, that is the shear strain between line elements E theta and E z, right. Okay, so, that is about the strain matrix in cylindrical coordinate system. The next question that comes is how to relate stress matrix and strain matrix in the cylindrical coordinate system. Okay. So, relating stress and strain the stress matrix. So, we have sigma r r, tau r theta, tau r z, tau r theta, sigma theta theta, sigma z z, tau theta z, tau theta z, tau r z. Similarly, the strain matrix we also know now. So, this has epsilon r r, epsilon r theta, epsilon r z, epsilon r theta, epsilon theta theta, epsilon theta z, epsilon r z, epsilon theta z, and epsilon z z. So, we have used that it is symmetric, and we have to relate these two. Again, assuming that the material is isotropic, then we know that the relationship is independent of the direction. So, we had the relationship in the Cartesian basis, is not it? We had sigma 1 1, sigma 2 2, sigma 3 3, relating them to epsilon 1 1, 2 2 and 3 3. But here we have the components along E r, E theta, E z. But if it is isotropic, the relationship is independent of the direction. So, this means we could choose any set of 3 perpendicular direction and resolve our stress and strain in those 3 directions, and the relationship would then be identical. The mathematical form of relationship would be identical. For example, we know that epsilon 1 1 is 1 over E times sigma 1 1 minus nu times sigma 2 2 plus sigma 3 3. And since the relationship has to be identical, this implies epsilon r r is 1 over E times sigma r r minus nu times sigma theta theta plus sigma z z, because the form of relationship has to be identical for isotropic bodies. If it is not isotropic, then of course, things get a bit complicated. Likewise, epsilon theta theta, that would be 1 over E times sigma theta theta minus nu times sigma r r plus sigma z z, and epsilon z z is then 1 over E times sigma z z minus nu times sigma r r plus sigma theta theta. And then for the shear strains, so gamma r theta is tau r theta by g, gamma r z equals tau r z by g, and finally gamma theta z is tau theta z by g. Okay. Likewise, you could also think of the relationship using lambda and mu, the Lamis constant. It is not difficult to figure it out, all right. So, that is the relationship between stress and strain. So, this completes our derivation for the representation of stress and strain in cylindrical coordinates, then the equations in cylindrical coordinates. in the next class we will use this to solve very interesting problems. For example, we will talk about stretching a circular bar, we will talk about twisting a circular bar, we will talk about pressurizing a hollow bar. So, when we stretch or twist or pressurize a hollow bar, what is the displacement that generates in the bar, what is the stress that generates in the bar, and you will see that using cylindrical coordinate system will make the solution easier. If you start using Cartesian coordinate system, the solution is very difficult, but in cylindrical coordinate system you will get many zeros, many equations will get automatically satisfied. So, things reduces and becomes easier. Okay. So, with this I will close the lecture today and see you in the next class. Thank you.